Continuing on in section 3.4, this is our first instance where we're not going to get to a nice base for both sides of the equation. So again, the first thing we have to do is isolate the exponent. So I'm going to subtract 13 to the other side. So I would get 47. And so if I have 2x equals 47, 47 cannot be written as 2 to a power. So this is where our problem lies. So what we need to do is use a logarithm. Now I'm going to do this a couple different ways because I just want to show you that they're all possible and to use some of the things that you should have used last week. So first, I'm just going to take log base 10. So I use log base 10, and remember we don't have to write the base for log base 10 of both sides. And when I do that, you might recall that there's a rule that says if there's a power on the argument inside of the log, I can bring that down in front of the logarithm. So I can rewrite the left-hand side as x times the log of 2 equals log 47. Then if I want to get x by itself, I would just need to divide the log 2 to the other side. So x equals log 47 divided by log 2. So I'm going to leave that as my answer because I don't want an approximation, but let's go ahead and find one just to see. So we'll use log of 47 divided by log of 2. And I get something like 5.5545, blah, blah, blah. Who cares? Right? It's just a continuing decimal. So how else could I do that? Well, I don't have to use log base 10. I can use, say, a natural log, right? And the reason we use log and natural log is they're both very common, and also because, as you'll notice, they have their own buttons on the calculator. So back at this step, we could have instead taken the natural log of both sides. Same thing, we can bring the x down in front. And then to get x by itself, we would divide by the natural log of 2 to the other side. So this looks almost exactly the same. And if you do these individually, you'll notice that log of 47 is not equal to the natural log of 47. It just happens that the division of the two is the same. So you still get 5.554588852. All right, so you could use log base 10. You could use natural log. And I'm going to go even further and do one more. All right, so I'm going to do at this step, I'm going to take log base 2 of both sides. And I'm going to do that because log base 2 of 2 to the x are inverse functions of one another. So log base 2 and 2 cancel, and I just get x. Now, that might look nicer, but we don't really know what that is, and we also can't put that in the calculator. And you might recall last week that you did change of base formula. So change of base says that this is equal to the log base anything else. Let's use log base 10 of the interior divided by log base 10 of the original base. And if you look, right, that's exactly what we had before. So I thought that's a nice little way to kind of tie everything together there. Let's go ahead and try some more. So let's move on to F. All right, as always, very first thing I would like to do is isolate the exponent. So I'm going to subtract 5 from both sides. And that's going to give me 22 over here. Then I need to get the 7 over, so I need to divide by 7. So I have 5 to the 5x minus 6 equals 22 sevenths. Okay. Should be pretty clear. It's not going to be nice for me to try to write 22 sevenths as 5 to a power. So I am better served in taking a log of both sides so that I can take that power and put it down in front. I think I'm going to use the natural log here. Right? Again, it doesn't really matter what you use, just that you're consistent on both sides of the equation. So I'll use natural log of both sides. That's going to allow me to bring that power down in front. So 5x minus 6 times the natural log of 5 equals the natural log of 22 sevenths. Okay, still trying to get 5x minus 6 by itself so that we can eventually get x. I would divide both sides by natural log of 5. And they'd cancel on the left. So I have 5x minus 6 is the division of 2 logs. Now be careful, right? If you remember, there are log properties, but one of them is not when you divide 2 logs. All right. Still trying to get x by itself. I need to add 6 to the other side. So let's come over here. So I'd have 5x equals natural log 22 sevenths over natural log 5 plus 6. And then finally, I have to divide everything by 5. But instead of writing it that way, I think I'm going to write times 1/5 of everything. And that is my exact answer. And if you like, you can punch that in the calculator. I'll do that quickly. So let's see, 0.2 times the quantity, natural log 22 sevenths divided by natural log 5 plus 6. And it looks like the approximation to this is 1.34 and a bunch of other numbers, but let's just truncate it there. All right, so if I ever typically ask you for something, it's going to be the exact answer rather than the approximation. All right. Let's continue. Now here we have base E. So in this case, we are definitely going to want to use natural log because natural log and e to a power are inverse functions. So first thing, let's get e to the power by itself. So let's subtract 5 on both sides. So I get e to the x plus 2 is equal to -3. Then I would like to get rid of the e. So I'm going to take natural log of both sides. And when I do that, right, this doesn't look good. Can I have the natural log of a negative number? If you think back, looking at the domain of logarithms, if you wanted, you could do a look at a quick sketch of one, right? A natural log or a log looks something like this. And so you'll notice that the values for x being negative are not allowed. And so if that's not in the domain, right, I can keep solving this. I can cancel out the log and e and solve for x. But because I have this log of a -3 here, I can jump right to no solution. And that's because the -3 is not in the domain of a log. And in our case, natural log. So it is possible that you run into a situation where there is no solution. All right, so this one here is not going to work out very nicely. By that, I mean the answer is going to not be very pretty. but we got to see, how these things work out from time to time. So first off, we got to get this exponent with the x by itself. So I'm going to subtract 10 from both sides. So I have 8 times this exponential, and then this is going to be 50 over e squared minus 10. Now, if you want, you can make that a whole fraction. So I could do this, or I could make it this way, or I could make it this. Whatever you prefer. I'm going to go with the first one I came up with here. So right now I have this. Okay, and I'm going to divide by 8 on both sides. So I have e to the 2 minus 3x is now equal to all of this. So now I need to take the natural log of both sides so that I can get that exponent down and solve for the x. And technically you could use any type of log, but natural log here is our best choice because the natural log and e are inverse functions. And so we just get those to cancel on this side. And we have this. Right? So now I need to subtract the 2 to the other side and divide by -3. So I'm just going to come up here where I have some room. So it's natural log, all of this, minus 2. And then finally divide everything by -3. And I'm going to write it like this. That would be my answer. And no, that is not pretty, but that is the answer. All right, so this example here is actually going to require that we do some factoring. So you might recall that e to the 2x is the same thing as e to the x squared. So if I rewrite it that way, right, e to the x squared minus 5 e to the x plus 6. Then what I can do, if it helps, is say let's do, I don't know, y equal e to the x, just for a second. So if I substitute that in, I get y squared minus 5y plus 6 equals 0. And now it looks normal to me in terms of factoring. So I need two numbers that multiply to 6 and add to -5. So that looks like that's going to be y minus 3 and y minus 2. At this point, I can go ahead and replace the y's with e to the x. So this is e to the x minus 3, e to the x minus 2. And then, of course, if either one of them could be 0, that means I can set them individually to 0 and solve. So this gives me e to the x equals 3. And to get rid of the e, I need to take natural log of both sides. And when I do that, these cancel. And on the left-hand side, I just get x. So I get x is natural log 3. And if I do this one, e to the x minus 2 equals 0, move the 2 to the other side, take the natural log, and then the log and the e cancel again, and I get x equals natural log of 2. Okay, so those are our two solutions to this quadratic equation. All right, and our last example of this type is another factoring example, but this time we might not have to make that substitution. We know that we're looking for two numbers that multiply to -8 and add to -7. So it sounds like -8 and +1 allow us to do that. And just like last time, we're going to get e to the x and e to the x, because we know e to the x times e to the x is e to the 2x, right? You add those exponents. So it has to factor this way. And we said the numbers were -8 and +1. And again, if I solve each one of these set to 0, then I will get e to the x equals 8. And then I take natural log of both sides. And over here it cancels. And I get x equals natural log 8. And on this side, I get this. Take natural log of both sides. And I'm hoping that your alarms are going off because I just got natural log of a negative number, right? This does not exist in the domain, and therefore this is not a solution. So there's only one real solution to this. And it looks like it's natural log of 8.